talk to you soon. I have let's see, I have a few of your students in trig. Who do I have? I have Steven Asensio. He's doing pretty well. You can say hi to Steven. He'll probably watch this. Can't remember who else, but I'll let you know afterwards. And Arlene says hi. She says she wants you to come to her graduation. Said you would. Be mad at her if she graduates. Yeah. All right, we'll do. See ya. Hey everyone, it's 6:28. I just got off the phone. My friend, formerly of Pioneer, Mr. Dinkman, and I am ready to get started in a minute or two. When you get in, please say hi so I know you're here, and I'll make sure that the sound is. They probably don't have the sound working. Okay, so no one in. Oh, great. All right, now I'm wearing the microphone. Can you guys hear me? Should be 3 people watching. We're about a minute till we get started. How's the sound? Cool. Pablo and Shiva can both hear just fine. Great. And we've got another person. 4. Sweet. Who else is here? Okay. That's 6:30. There's only 4 of you so far, but I suppose others can watch after it records, and I'm sure we'll have a few more joining us at some point. According to Shiva and Pablo, the sound is just fine, so hopefully that's true. My plan for tonight is to go over that chapter 8 chapter test in your textbook that I recommended for review today in class. If there's other things you'd specifically like me to go over, please let me know. If at any point as I'm going over a problem you have questions, please let me know. For those of you who are here now, Shiva and Pablo, and some third as yet unknown student, are there any questions you already know you have that you want me to go over? Perhaps any that are not in the chapter test or any that I particularly need to focus on in the chapter test? Shiva says no. Great. That's easy. Of course, the students who come to the review session are the ones who don't actually need any review. That makes sense. No, I'm kidding. I'm messing with you. Acidic Hazel. I love that name. Can you go over the deriving and using the trig ratios for special right triangles? I would love to do that. That sounds like a brilliant question. I would be happy to do that, Acidic Hazel. Cool. Should we do that to start with then? Let's do that to start with. So special right triangles. And Steven says, oof. Steven, Mr. Dinkman says hi. I was just talking with him. Oh, and Lindy está aquí. Muy bien. Okay, so we had a request to go over the deriving and using the special right triangle ratios, which I will do before I get to the Chapter 8 review materials. So the special right triangles, there's the 30, 60, 90, and the 45, 45, 90. Oh, and I just have to look at something. I want to see. I'm sorry to be distracted, but I had this email that looked like it was from Tim Zolinardo, and they even got his name right, and it just says, "Are you available?" But then the email here is headofschool95401@gmail.com. So it's clearly not Mr. Zolinardo. And then I said, I didn't notice at first. So I said, oh, yeah, I have a few minutes. I'm in my classroom. And then it was pretty clearly spam because it says, okay, I'm contacting you via my email because I don't have access to my phone for now. I want you to help me out on something very important. And at that point, I was like pretty clear that it was spam. But I haven't heard back from them. I'm really excited to see what they say next, though. I've never had a spammer like actually continuously contact me. Anyway, sorry to be distracted. And we're going to talk about some vectors, says Acidic Hazel. We can do that. Vectors sound good. Probably do that after I go over some of the Chapter 8 tests in your textbook. So 45, 45, 90 looks like here and here. And this is going to be 45, and this is going to be 45, and it's 90 degrees. And that means that we know that these two sides are always the same. So that's x and x. And then the goal here is to find the third side. So we can say by the Pythagorean theorem that x squared plus x squared equals c squared, which means that 2x squared equals c squared, which means that, let's see, c equals the square root of 2x squared, so c equals x root 2. So we can come back in here and say x root 2. Well, now I know the ratios of all three sides of the 45, 45, 90 right triangle. So from there, I can find all of the trig functions of the 45, 45, 90 right triangle. So I can say the sine of 45 degrees is equal to opposite over hypotenuse. So x over x root 2, which is 1 over root 2, which is root 2 over 2. And the cosine of 45 degrees, which is going to be the same because the function and the cofunction, 45 and 45, same angle, root 2 over 2. And the tangent of 45 degrees is equal to x over x, which just equals 1. And quickly now, the cosecant of 45 degrees is equal to hypotenuse over opposite. So x root 2 over x, which just equals root 2, and the secant of 45 degrees, same thing, and the cotangent of 45 degrees equals 1. And let's say I perhaps had a math problem. Well, let's go do the 30, 60, 90, and then we can do some example problems. So 30, 60, 90, I've got a triangle that looks like this, and this, and there. And it's got 90 degrees, and 30 degrees, and 60 degrees. And I know that the 30, 60, 90 triangle was 1/2 of an equilateral triangle. So I could say, here's the other half of that equilateral triangle, where this was also 60 degrees, and this was also 30 degrees. And since this whole thing is an equilateral triangle, and this is half of the equilateral triangle, this side must be half of this side. So I can write that in there by saying this must be x and 2x. And then I'd like to solve for side B. So I'm going to use the Pythagorean theorem again and say x squared plus b squared is equal to 2x squared. So that x squared plus b squared equals 4x squared. So that, minusing x squared from both sides, I have b squared equals 3x squared. And b equals the square root of 3x squared, and b equals x root 3. So I can come back to my diagram and say, now I've got x root 3. Now that I know all of the ratios of my 30, 60, 90 right triangle, I can go ahead and express all of the trig ratios. So we can do, I'm going to go ahead and do just sine, cosine, and tangent for 30 and 60. So sine of 30 equals the opposite over the hypotenuse. So from 30 degrees, that's x over 2x, which is 1/2. And the cosine of 30 degrees equals the adjacent over the hypotenuse. So x root 3 over 2x, which is root 3 over 2. And the tangent of 30 degrees is equal to the opposite over the adjacent. So x over x root 3. So 1 over root 3. So root 3 over 3. And then how about the sine of 60 degrees, which is opposite over hypotenuse. So x root 3 over 2x. So root 3 over 2. And the cosine of 60 degrees is equal to adjacent over hypotenuse, x over 2x, so 1/2. And the tangent of 60 degrees is equal to x root 3 over x, so root 3. Alrighty. So now, well, how about I combine, I remember Hazel had just a question in general about vectors. So why don't I do some of those vectors problems that I recommended, because they are good applications of your 30, 60, 90 ratios, and they're in section 9.4 right here. Okay. So here on number 55, there's a vector v with magnitude 5 and an angle with respect to the positive x-axis of 60 degrees. And our job is to find how much does that vector go over and how much does it go up, which is to say, let's write it in its AI plus BJ form, its unit vector form. So this is 5. So I can say, all right, I have a little model triangle that I just made that tells me all of the ratios of the 30, 60, 90. So let's draw in that model triangle. Here's my model triangle. It said if this is 60 and this is 30, then the ratios will be x, 2x, x root 3. So I can see here that 5 is the same as my 2x side. So if, kind of some side work here, if 2x equals 5, then x equals 5 over 2. So I can come over here and say this is 5 over 2 I hat. And then saying if x equals 5 over 2, then x root 3 must be 5 root 3 over 2. So I got that side. And that means that this here must be 5 root 3 over 2 j hat. So the answer to number 55 is vector v equals 5 over 2 I hat plus 5 root 3 over 2 j hat. And that's a pretty nice illustration down here of how to use the 30, 60, 90 ratios to solve a triangle. How'd I do, acidic Hazel? Did I answer some of your questions about deriving and using the trig ratios for special right triangles and vectors? Sure. Sure. Okay. Well, sure isn't particularly committing, but we'll go ahead and take it for now. And then maybe I'll do some of the chapter 8 practice test. And then if we have more time, oh, bummer. If we have more time, we can come back to that near the end, I suppose. So returning to, here's my chapter 8 practice test. Okay, so it starts out with defining the trig ratios in right triangles, which is your first core standard for our course. And let's see, we've got 3 and 6. It's going to be kind of nice to know the hypotenuse. So I'm going to call this hypotenuse C. And if A was 3 and B was 6, then A squared plus B squared equal to C squared tells us that 3 squared plus 6 squared equals C squared. So 9 plus 36 equals C squared. So 45 equals C squared. So C equals the square root of 45. So C equals, what is that, 3 root 5? Good. C equals 3 root 5. Now I need the 6 trig functions. So sine of theta, cosine of theta, tangent of theta, secant, well, let's do cosecant next, of theta, secant of theta, and cotangent of theta. So the sine of theta is equal to the ratio of the opposite side to the hypotenuse, which is, in this triangle, 3 over 3 root 5. Which reduces to 1 over root 5, which reduces to root 5 over 5. Or simplifies to, I suppose I should say. The cosine is the ratio of the adjacent to the hypotenuse, which equals 6 over 3 root 5, which equals 2 over root 5, which equals 2 root 5 over 5. Then the tangent of theta is equal to the opposite over the adjacent, which equals 3 over 6, which equals 1/2. The cosecant of theta is equal to the ratio of the hypotenuse to the opposite, which is 3 root 5 over 3, which is root 5. The secant of theta is equal to the hypotenuse over the adjacent, which equals 3 root 5 over 6, which equals root 5 over 2. And the cotangent of theta is equal to the adjacent over the opposite, which is 6 over 3, which is just 2. Cool. Questions on number 1. Okay. Seeing no questions from the 6 of you gathered here, let's go on to number 2. Find the exact value of sine 40 minus cosine 50. This is an extended standard, the first extended standard, about the relationship of the sine and the cosine of complementary angles. You want to not be able to just plug it into the calculator, but actually be able to explain and write a sentence about the relationship between the sine and cosine of complementary angles. So here we have a 40-degree and a 50-degree angle. So I'm going to draw a triangle, and I'm going to give it approximately a 40-degree and a 50-degree angle. So there's 50 degrees and 40 degrees. And I'm going to label these sides, side A, side B, and side C. And I'm going to note that the sine of 40 degrees minus the cosine of 50 degrees is the same as doing, let's see, sine of 40 would be A over C minus the cosine of 50 is A over C. And A over C minus A over C equals 0, which is certainly your answer. On your test, you might want to be able to say something like the side opposite 40 degrees is always adjacent to 50 degrees. So sine of theta is always equal to cosine of 90 minus theta. And so let's go back in here and say side opposite. How about any angle theta is always adjacent to any angle theta minus 90. So sine of theta equals the cosine of 90 minus theta, and therefore sine of 40 degrees equals cosine of 50 degrees. And you could switch the degrees and get the exact same answer. The sine of 50 would always equal the cosine of 40, 100%. That is what the cofunction of a complementary angle means. I think we should reiterate that this was our original definition of cosine. Cosine is the sine of the complement, which is why the opposite in sine switches with the adjacent in cosine, because the side that is opposite from some angle would always be adjacent to the complement. That's what the co in cosine means. Anyway, good stuff. Yes, Hazel, definitely. Switching the degrees would give you the same answer. There's lots of ways you could write that same question. Any other questions about number 2? Okay, I'm pretty sure that's about it or getting close to it for the right triangle problems on this practice test, because a lot of what's in here is the unit 2 stuff, the law of sines, law of cosines situation. So let's go on to number 3. So we have in number 3, 2 sides and an angle of a triangle, and we have to solve for the other side and the 2 angles. And we're probably going to want to use the law of cosines, which says that in this triangle, where I'll call this side B and this side C, and this angle A, that A squared should equal B squared plus C squared minus 2BC cosine of angle A. And therefore, A squared must be equal to 17 squared plus 19 squared minus 2 times 17 times 19 times the cosine of 52 degrees. And I can't do any of that in my head, so let's go ahead and grab a calculator. So we want to know side A, and it's going to be equal to the square root of 17 squared plus 19 squared minus 2 times 17 times 19 times cosine of 52. And let's make sure I'm in degree mode. Looks like side A is 15.88. Great. Okay. I'm going to go ahead and go in alphabetical order. So I'm going to find angle B next. So this was solving for side A, 15.88. And now for angle B. Well, angle B, I think I now have all three sides, so I certainly could use the law of cosines to find angle B, but I think the law of sines is easier. So I'm going to go ahead and use the law of sines. So I'm going to write that the sine of angle B is equal to, sine of angle B over its opposite side, 17, is equal to the sine of angle A, 52 degrees, over 15.88, which means the sine of angle B is equal to 17 times the sine of 52 over 15.88, which means that angle B is equal to the inverse sine of 17 sine of 52 over 15.88, which I will now plug into the calculator. Solving for angle B, which is equal to the inverse sine. Oh, there we go. Of 17 sine 52 over side A. So 57.5 degrees. Angle B is equal to 57.5 degrees. And now to find angle C, I know that all the angles in a triangle add up to 180. So 52 degrees plus 57.5 degrees plus angle C equals 180. So angle C must be equal to 180 minus 52 minus angle B, 70.5 degrees. Is angle C. Rockin'. Any questions on number 3? I'll wait for questions while I get set up on number 4. Number 4 definitely looks worth doing. I am noticing that we're at like 7:01. Still got a full hour. So I think I'll probably just keep going. But at some point I may want to switch and jump to anything that someone had like particular questions about. Oh, whoops, that's not the one we're supposed to do next. Where's the one we're supposed to do? Oh, I didn't even grab it. Just because I don't want you guys to miss something you really need if we run out of time. And I am going to stop at 8. Okay, so here's number 4. I've got angle, I'm going to call this, let's see, call this angle A, it looks like, and this angle B, and this is angle C and side C, and this can be side A. And this looks like a good opportunity to do the law of sines. I'm going to say, first of all, I'd like to solve for angle C. And I know there's 180 degrees in a triangle. So that means that 180 minus 41 minus 22 is equal to 117. So angle C equals 117 degrees. And now I want the sine of 41 degrees over 12 to equal the sine of angle C, which we just found was 117 degrees, over side C. So this is going to be for side C. Okay, which means that, well, let's see. If I cross multiply, then C times the sine of 41 degrees is equal to 12 sine of 117 degrees. And that means that C is equal to 12 sine of 117 degrees over the sine of 41 degrees. And there we go. So let's go ahead and figure out what that is. This was angle C. And now I'm at side C, and it's 12 sine 117 over sine 41. So 16.30 I'll round to. C equals 16.30. And last thing here is I'm going to find side B. And to find side B, I'm going to go sine of 41 degrees over 12 again is equal to the sine of 22 degrees over side B, such that B times the sine of 41 degrees would equal 12 sine 22. And B would equal 12 sine 22 over sine 41. So I'm going to go ahead and change that to a 22. And find out that B equals 6.85. There we go. Good law of sines practice. Okay. I remember that Shiva asked me about number 7, and it was kind of a funky problem. So I think we should talk about number 7 for sure. And then I'm thinking I might jump to some of the area or some of the word problems. I think numbers 6 and 8 are pretty easy, and number 5 is pretty easy. And I want to make sure I have time for some of the harder ones. So let's go to number 7. So number 7, we have a triangle with a side A equal to 3, a side B equal to 7, and an angle A equal to 40 degrees. And I'm going to say, okay, there's my 40 degrees. There's my side A equal to 3, and my side B equal to 7. So this is angle A, this is side A, this is side B, here's angle B, here's angle C. And I see that I have a law of sine situation. So I'm going to go for angle B first, and I'm going to say, all right, the sine of 40 degrees over 3 ought to equal the sine of angle B over 7, which means that the sine of angle B equals 7 times the sine of 40 degrees over 3. And just to illustrate a point, I'm going to go ahead and calculate 7 sine 40 over 3 right now. 7 sine 40 over 3. And it's 1.499. We'll say 1.5. And right here, this ought to cause us cause for concern. The sine of an angle is the ratio of the opposite side to the hypotenuse. So just to kind of give a reference over here, I'm thinking about, here's my angle. Okay, here's my opposite side, and here's my hypotenuse. And according to this, the ratio of the opposite side to the hypotenuse should be 1.5. Well, that means that the opposite side should be 1.5 times larger than the hypotenuse. How am I going to get the opposite side to be larger than the hypotenuse? Well, I can try and redraw it. I need a larger opposite side. And the best I can do is something like this, where I've got opposite and hypotenuse. But still, the hypotenuse is the longest side in the triangle. No matter how I redraw that triangle, the hypotenuse is always the longest side. It's impossible for me to get an opposite side that's larger than the hypotenuse. And next quarter, when we start talking about functions, we'll phrase that truth by saying that 1.5 is outside the range of the sine function. The sine function only goes up to 1. The best you can get is the opposite side equal to the hypotenuse. You can't get the opposite side bigger than the hypotenuse. And since the 1.5 value is outside of the range of the sine function, that means it's also outside of the domain of the inverse. So 1.5 is not something we can evaluate in the inverse sine function. You cannot take the inverse sine of 1.5 because the ratio of the opposite to the hypotenuse could never be 1.5. And we find that out, kind of hits us in the face when we come here and we try to say, what is the inverse sine? We know that angle B ought to equal the inverse sine of that 1.5. So I ought to be able to come in here and say, okay, what's the inverse sine of this? And it's undefined. It doesn't exist. Can't be done. Error. And the reason this whole thing makes this error is because I didn't know ahead of time. Well, I actually did know ahead of time because we just talked about it today. But I wouldn't have known ahead of time that this triangle wouldn't work. But now I can go back and see that if I was being precise and I drew 40 degrees and I made that 7, 40 degrees, that actually 3 would only go like that. That would be 3 units long. And it's actually impossible for 3 to come and hit this opposite side. So this is not a real triangle. This here is not a triangle. It's impossible for those measurements to form a triangle. You can't have a triangle with a side of 3 and 7 and an angle of 40 degrees opposite the 3 side. That's impossible. It doesn't work. And we find out that it doesn't work right here when we get this error. Cool. Questions? That was a little tricky. Good thing to notice, though. Yeah, and this is connected to that kind of overall piece, which we haven't really concerned us because it's not of a huge concern to our course, but that this is part of this question of kind of the ambiguity of the law of sines, that we know we've already come across the idea that the law of sines can't give an obtuse answer. Thus, it was not proven. I love it. QEND. Thank you. Yeah, and this is the same case of the side angle situation where you might get 2 triangles, you might get 1 triangle exactly, and you might get no triangles. There might be no way to get the inverse sine. You might get 2 angles possible out of the inverse sine because you know the obtuse one doesn't come out, or you might get 1 angle out of it. And this, it's not a huge deal. It won't be on the test. It did come up in the text a couple of times. It's never a huge important issue. We have to know that we can't get obtuse angles from the law of sines. And here was a situation where we tried it and we're like, oh, cool, an error. Can't happen. Great. Let's do number 6, just to actually solve a triangle that was written out to a problem that was like that, but actually get a real answer, not no answer. So coming back to number 6. Oh, didn't grab it. There it is. So on number 6, we have an angle A equal to 55 degrees, an angle C equal to 20 degrees, and a side A equal to 4. So angle A, 55 degrees, a side opposite equal to 4. Ooh, and I got to make a side C equal to 20 degrees. That's not going to really work. 55. Let's go like that. That's better. That's more like 20 degrees. Okay, and this equals 4. So this is 20 degrees. C, angle A, 55 degrees. This is going to get to be angle B, and side A equals 4, side B, side C. Okay, and I'm thinking law of sines again. Lots of good practice with the law of sines. So sine of 55 degrees over 4 is equal to the sine of 20 degrees over C. So that means that C times the sine of 55 degrees is equal to 4 sine of 20 degrees, which means that C equals 4 sine 20 degrees over the sine of 55 degrees. So, scrolling down a little bit. Oh, let's just plug that in. C equals 4 sine 20 over sine 55. C, side C, equals 1.67. Go back to our diagram. That looks pretty reasonable. C equals 1.67. Alrighty. And now finding angle B. Well, this was, okay, so this is my work for side C. Here's going to be my work for angle B. I know that 20 degrees plus 55 degrees plus angle B should equal 180 degrees. So angle B equals 180 minus 55 minus 20, so 105 degrees. 105 degrees. And now I can finish by saying, to get side B, I will do sine of 55 over 4 equals sine of 105 over B. So that B sine 55 equals 4 sine 105. And B equals 4 sine 105 over sine 55. B equals 4 sine 105 over sine 55. 4.72. Okay, returning to my diagram. That looks highly reasonable. B equals 4.72. Great. Any questions on my work here in some pure math problems using the law of sines and the law of cosines? Nope, nada. Rocking, feeling good. Okay, any in particular word problems you guys want to do? Lindy says we should work on vectors. Okay, sounds good. So ditch that and do a vectors problem. Fair enough. Oh, Hazel says 11. Well, then before I ditch this into a vectors problem, let's do 11. Yeah, do 11 first. Good call. Okay. Number 11. A 12-foot ladder leans against a building. The top of the ladder leans against the wall 10.5 feet from the ground. What is the angle formed by the ground and the ladder? Ooh, a little return to right triangle trigonometry. Okay, so I'm making the assumption that this wall or this building is standing straight up, because pretty much whenever I lean ladders against buildings, I make sure to land them against buildings that are built well. So this is 12-foot tall ladder. Here's the ladder with the rungs. Like that. And here's the building. And here's the ground. And it's leaning against the wall 10.5 feet from the ground. So 10.5 feet high. 10.5. What is the angle formed by the ground and the ladder? So we're going to call that angle theta. And we're going to note that the sine of theta is equal to the opposite side, 10.5, over the over the hypotenuse, 12, which means that theta ought to be equal to the inverse sine of 10.5 twelfths. Not being myself a calculator, I need to use a mechanical calculator. So inverse sine of 10.5 twelfths. 61 degrees. 0.04. Since I'm reviewing, and this is the quarter one midterm test, I think I'll go ahead and note right now that I would hope that everyone would see this right triangle problem and be like, cool, I know the sine ratio, it's opposite over hypotenuse, I'm good to go. But let's say someone gets confused and is like, oh, maybe I'm supposed to use the law of sines. I know there's a lot of law of sines on this test. Let's just note that the law of sines would actually still work here, right? We could say, let's say I don't realize the situation that I should be just using the sine ratio, and I write sine of 90 degrees over 12 is equal to the sine of theta over 10.5, right? Let's just label here right triangle trig, best option. And here's law of sines, more work, but still correct. So it wouldn't make sense to use the law of sines here. It's just extra work, but it doesn't give us a wrong answer or anything. I'm going to get now that the sine of theta, and look at this, because this is kind of a good lead into next quarter, is I get 10.5 times sine of 90 over 12. And look how similar this is, right? Like here I said sine of theta equals 10.5 over 12. And look at what I arrive at here. Sine of theta equals 10.5 times sine 90 over 12. And why are these so close to the same? Well, we haven't defined sine 90. And there was a great question at one point in class where someone was like, what about 90 degrees? And we haven't actually built a definition that allows us to understand the sine of 90 degrees. But here we can see that because the sine of 90 degrees equals just 1, 90 degrees would mean that the opposite was the same as the hypotenuse. So the ratio of the opposite to the hypotenuse would just be 1. That 90 degrees doesn't do anything here. The law of sines doesn't mess us up. It just equals 1. And then I'm back to my right triangle trigonometry situation, which is sine of theta equals 10.5 over 12, right? Because that 1 doesn't do anything. Times 1 makes no difference. So I still get, in the end, sine of theta equals 61.04 degrees. Cool. You didn't really need to know any of that, but I just thought it was kind of interesting, so I just added it on. That, we could use the law of sines. It doesn't make sense to use the law of sines. I hope that you notice that this is a good opportunity for right triangle trig, which would always be easier than using the law of sines, but the law of sines wouldn't be wrong. We'd still get the right answer. Any questions further about number 11 before I ditch chapter 8, trigonometry, and look a little bit at vectors? Any others from chapter 8 that you want me to take some time with? Or does it sound good to go look at vectors a little bit? Okay, seeing no objections, let's go ahead and move over here to, in the last half hour we have, some good vectors problems. Okay, so let's see. There are some pretty good straightforward problems in this section, and there are also some really tough problems in this section. I'm happy to go over some of those tough ones. Like these static equilibrium problems regularly give kids a lot of trouble. These are tough problems. You have to use a system of equations. I've often spent a lot of time on trying to help kids understand these really tough problems, but I've kind of been feeling this year like some of the things that can take up a lot of time in trigonometry class, like the ambiguous case of the law of sines, or these system of equations, static equilibrium problems, aren't super worthwhile because they never really come back at all later on. In fact, for the rest of the year, we won't really use the law of sines or the law of cosines. So I'm hoping this year that I've kind of emphasized just using the law of sines and the law of cosines to do some problems, and that we've also got to continue our basic trig practice with sine, cosine, tangent, because the sine, cosine, tangent we really do need for a whole nother quarter. And those are going to be the things that are more useful later on in calculus. But anyway, I'm going to do one or two of these kind of better basic problems like 63, 64, 65, and 66. And then if you want me to, I can do one of these tough problems. These problems here are tougher than what would be on the test. These problems are good examples of what might come up on the test. So let's say, how about 63? Okay. A child pulls a wagon with a force of 40 pounds. The handle of the wagon makes an angle of 30 degrees with the ground. Express the force vector F in terms of I and J. So this is just decomposing a vector that's given in magnitude direction form into its unit vector form. So let's see. We've got a wagon. And it's got a lever. And the man's pulling with a force of magnitude 40 pounds. And we want to say how much of that force is pulling the wagon forward in the horizontal direction, and how much of that force is not really being used and is just allowing the man to use this handle, in which case he's pulling somewhat up, but that's not really helping him pull forward. So this is called decomposing, or finding the components of the vector. And it's really useful skill in a lot of physics problems, is to say what part or what component of this vector is actually going this way. Because if you had like maybe, this is a force, mass, acceleration, if you knew what component was pulling this way, you could know the acceleration in the horizontal direction. Because probably this wagon is not being accelerated in the vertical direction at all. It's only rolling in the horizontal direction. So you'd want to know about just this horizontal component of the vector. So this is a really useful skill, and it's a pretty basic problem. The handle of the wagon makes an angle of 30 degrees. Oh, look at that. It's a great opportunity to practice our 30, 60, 90 triangles. So let's go off here to the side, just like we did last time, and draw a little model triangle. 30 degrees, x, 2x, x root 3. So I can see here that the 2x spot looks like 40, which means dividing by 2 that x must equal 20. So I can come in here and say, hey, this is 20 j hat. And then I want to know what's the x root 3. So if x equals 20, then x root 3 equals 20 root 3. So this must be 20 root 3 I hat. So express the force vector F equal to 20 root 3 I hat plus 20 j hat. Cool. Hopefully no questions on number 63. It's a fairly straightforward problem, I think. Should we check out one where I don't get to use my nice 30, 60, 90 ratios? Still a very similar problem, but now I have to use a calculator. Okay. 64. A man pushes a wheelbarrow up an incline of 20 degrees with a force of 100 pounds. So here's an incline of 20 degrees. And the man's pushing the wheelbarrow. I'm not an amazing artist, but I kind of basically know what a wheelbarrow looks like. Struggling with my wheelbarrow drawing skills. I think it looks kind of something like that. And it's got handles coming off the side. And there's my dude. And he's pushing that wheelbarrow. There we go. That's pretty good. Pushes a wheelbarrow up an incline with a force of 100 pounds. Okay, so the force going this way is 100 pounds. Oh, I probably should come back here and say pounds. 20 root 3 plus 20j pounds. Be nice to include, those are the same units of force in the end. Okay. So now I want to again express the force vector in terms of I and j. So I want to know how much is there in I and how much in j. What portion or component of this vector is actually pushing forward in the horizontal direction, and what component of this vector is being pushed up in the vertical direction. Okay, and now I need a calculator because I can say clearly force F is equal to, here's this angle, 20 degrees. So cosine 20 degrees I hat, 100 cosine 20 degrees I hat, 100 cosine 20 degrees I hat plus 100 sine 20 degrees I hat or j hat. And just for clarity's sake, let me show how I know that. Oh, whoops, I closed. Let me show how I know that. Oh, I've hit the power button by accident. There we go. So I can say that I know that this is side. Well, let's do this side is x and this side is y. And I know that the sine of 20 degrees is equal to the opposite y over the hypotenuse 100, which is why y is equal to 100 sine 20. And I also know that the cosine of that 20 degrees is equal to the blue side x over the hypotenuse 100. And that means that x equals 100 cosine 20 degrees. So I'm taking that and putting it here, and taking that and putting it here. Lindy, you're worried about Xander getting here? Terrible news. So let's see, 100 cosine 20 is 93.97. So my vector F equals 93.97 I hat plus 34.2 j hat. Cool. Any questions on number 64. Oh, and I should include my units. Pounds of force. Okay. Seeing no questions, let's try doing some direction magnitude problem. Okay, so this is one of your Shiva, what worksheet are you talking about? The questions on the worksheet I gave you today? I didn't give you a worksheet today. Did I? What worksheet did I give you today? Oh, you mean for the whole section? Okay. For all of chapter 8 review. Those aren't in there? The one that we scored ourselves. Yeah, okay. But the worksheet where you scored yourself, all of the questions were from the assignment, page 558, 1 through 17 all, right? Wasn't that where I said to find all of the, oh no, all of the reviews, the whole review section, not just the chapter test. I see. I got you. Yeah, I can post some more answers for sure. You got it. I'll post the rest of those answers to the review section. Now I understand what you're talking about. The vectors answers too, or just the chapter 8 review questions? Oh well. We'll see. Anyway, 65. Direction magnitude. We want to find the sum of force 1 plus force 2, the direction and magnitude of the resultant force. So I kind of have a few options. Remember, we said we could either do a law of cosines problem where we drew in this vector here, and we said, all right, its sum would be what happens when I put that vector right here and draw the sum vector, which is like that. So I could do this as a law of cosines problem where I must know 30 and 75. So let's say this must be 105 degrees. And then I can say this is 40 newtons and 60 newtons. So this was 60 and this was 40. Sorry, I sneezed. Excuse me. And thank you, Hazel. Much appreciated. Once these days I use like a microphone, so I can like at least take the microphone off and sneeze away from the microphone. But I used to do them with no microphone, and so the it would just be the microphone on my computer, so you can't like actually get away from it very quickly. And I sneezed once so loudly, and like the whole group watching it all freaked out. They thought my house had like blown up or something. It was very scary for them. They talked about it for the whole rest of the year. Anyway, sneeze stories on the review sessions. Anyway, we can do this with the law of cosines by taking this side, this angle, and this side, or you can also decompose it into ij and decompose this one into ij, and then add the components separately, and then return to direction magnitude to find the purple vector. I think they're both equally good. You probably want to understand both. I'm going to go ahead and do both. I'm going to start with the law of cosine strategy for doing these problems. So one way is law of cosines. The other way is component form. So with the law of cosines, I'm going to first find the magnitude. So I'm going to say if this is side C, so C squared equals 60 squared plus 40 squared, 4D squared minus 2 times 60 times 40 times cosine 105. So C equals the square root of all of that. Forty cosine 105. 80.2. And now I want to know this angle, because that's the direction angle for this vector, and it's going to be a negative direction angle. But in order to get this angle, I'm going to go ahead and find this angle and then subtract. So I'm going to use the law of sines, and I'm going to say sine of theta. So I'm finding this theta here right now. Theta over 40 equals sine of 105 over C. So that sine of theta equals 40 sine 105 over, let's see, C is 80.2. 80.2. So that theta equals the inverse sine of 40 sine 105 over 80.2. Inverse sine of 40 sine 105 over C. 28.77 degrees. So theta equals 28.77 degrees. And then I'm going to come back in here and say, okay, this was 28.77 degrees. 28.77 degrees. And now I want to find this alpha, and it's going to be 45 minus 28.77. So 45 minus, let's call this one theta, and 45 minus that is 16.2. Okay. and it is negative. So our final answer then is F1 plus F2 equals negative 16.2 degrees with a magnitude of 80.2. Cool. And now I'm going to do the same thing in component form. So decomposing vector F1, vector F1 is a 30, 60, 90 triangle. So F1 is going to be like here and here. And that's going to be, let's see, 30, 60, 90. I'm talking about 20 root 3 I hat plus 20 j hat. And force 2 is equal to, well, it's a 45, 45, 90 triangle. So I'm thinking 30 root 2 I hat minus 30 root 2 j hat. Does everyone know that this comes from that 30, 60, 90 ratio? And these come from that 45, 45, 90 ratio? Can everyone picture that? Should I zoom in and show that more clearly? Here we went up, sorry, over and then up. And this is 30, 60, 90. So this side had to be, if this is 40, then that's 20, and that's 20 root 3. That's why I got 20 root 3 and 20. And in here, over and down in the 45, 45, 90. And this was 60. So this has to be 30 root 2 and negative 30 root 2. All right. Lindy understands it. We're good. Okay. And now F1 F plus F2 equals, well, 20 root 3 plus 30 root 2I plus 20 minus 30 root 2j. Okay, but it said explicitly find the direction and magnitude of the resultant force. So don't find the component form of the resultant. I now have to go get the direction and magnitude. So to find the direction, magnitude first, I'm going to say, all right, a squared plus b squared equals c squared. So that's going to be the square root of 20 root 3 plus 30 root 2 squared plus 20 minus 30 root 2 squared. So square root of 20 root 3 plus 30 root 2 squared plus 20 minus 30 root 2 squared. 80.26. So equals 80.2. Same as we got last time. And for the angle, we're going to do the inverse tangent of the opposite, 20 minus 30 root 2, over the adjacent, 20 root 3 plus 30 root 2. Inverse tangent of 20 minus 30 root 2 over 20 root 3 plus 30 root 2 is negative 16.2 degrees. Same as we got last time. Alpha equals negative 16.2 degrees. So we find, again, that F1 plus F2 equals negative 16.2 degrees at 80.2 magnitude. Hurrah! Which brings us right to the end of our time together. Any final questions before I go? QED, that's right. Thank you, Lindy. Agreed. That's a good question, Xander. When would we use one strategy or the other? I would say in this problem, I in general prefer the law of cosine strategy for these problems. I find it to be slightly shorter. You'll see, to me, this looks like less work than all of that, personally. But if there was ever a time where I would prefer this form, it would be maybe here where it's a nice 30, 60, 90 and 45, 40, 90. So that it comes out a little nicer. Then I might be a little tempted to do this. But this to me still seems easier. I'm for this way. In general, I find the law of cosine strategy to be easier, but I think conceptually it's maybe harder because you have to visualize a little better. And here, I think it's more mechanical. There's less visualization required. So maybe more people prefer this way. This is explicitly one of the standards you're supposed to know. It's an extended standard for Unit 2. So you don't have to know this to pass, but you would have to know this to get an A or a B. I think the standard reads, I don't have any of those standard sheets sitting around, but it's add two vectors in direction and magnitude form and find the direction and magnitude. So this is a problem exactly like this is likely to be on the test for sure. But Hazel, if you don't know it, if you know the other stuff is all core standards. So this is extended standard. I wouldn't be worried about it. If you don't know it, you don't know it. It's only going to hurt between like an A or a B. It's not crucial to passing the course. But something, Lindy, like this is likely to show up. Cool. You guys feel good? Ready for Friday? Feel free to come in tomorrow after school if you have more problems you want me to go over. Anything on this review session you didn't understand, anything like that. I'll be here tomorrow. I think it's nice we got to do this tonight so everyone has a chance to watch tomorrow or between today and tomorrow and can ask me questions if you have further questions about anything I did here. Anyway, I'll see you guys all Friday for a quarter 1 exam. talk to you then. Good night.